Hi, I'm Clifton Cunningham, and welcome to this introductory talk on Arthur packets. This talk is background for a talk on September 9th, 2020 on unipotent representations for the p-adic group for G2 over p-adic fields, and their Arthur packets specifically. So in this talk, I'm merely going to describe fundamental properties of Arthur packets or A packets, as they're known for other groups, namely the classical groups that are treated in Arthur's book. I should mention, of course, that these results have been extended to unitary groups by the work of Chumping, Mock, and others. So that's the context you should keep in mind for this talk. In the background, G will be, in fact, for simplicity, G will be a split orthogonal or symplectic group. And F will be, in fact, a p-adic field. So Arthur's main local result from his 2013 book on the endoscopic classification of representations introduces A packets. Well, in fact, that's not true. A packets were introduced globally in 1989 in a couple of papers that Jim Arthur wrote where the ideas first appeared, but really it was in this book that many of the conjectures from those papers were established, and we find the fundamental properties of local A packets in particular are articulated, as in this theorem. So the finite set pi tilde sub psi that you see right there, that's an A packet, and psi is what's known as an Arthur parameter. I'll fill in some of the gaps in the way I'm introducing this theorem right off the bat little later in the talk. But for now, I'd like you to just see the statement of the result. The statement, the form of the result, I should say. Here we see that the finite set, the A packet, comes equipped immediately with a function from the A packet to the set of characters of a finite group S psi. This group is abelian in the case of the groups that we're talking about, and so I'd like you to think, even though it might seem a little ridiculous, I'd like you to think of S hat as characters of irreducible representations of S psi. The reason for that is that, as we'll see in the next talk, S psi need not be this finite group, need not be finite, need not be abelian, I should say. And in fact, G2 is a fun group to play with, precisely because it's the first group for which we see non-abelian groups appear in this way. So the A packets come equipped automatically with this function from A packets into characters of a finite group that's attached to the Arthur parameter. And this function, we see in part B of this theorem, this function is in fact a bijection if the Arthur parameter is, well, way to think about it is to say that the Arthur parameter is tempered in the sense that it's trivial on the third component in the definition of its domain, which I'll review. And in this case, we know that the A packets, the representations appearing in the A packet are all tempered, and all tempered representations appear in such A packets. So A packets, they coincide with L packets in this case, give you a partition, in fact, of the set of tempered representations, tempered admissible representations of GF. In general, however, for arbitrary A parameters, this function from the A packet to characters of S psi is neither injective nor surjective. Well, let's back up for a moment. Let's talk about the Langlands correspondence. The A packets somehow are designed, in fact, to shed light, I would say, on the Langlands Correspondence. And in fact, from the perspective of Arthur's book, it's exactly how we established the Langlands Correspondence for classical groups. So the Langlands Correspondence classically is articulated as a surjection from the set of equivalence classes of irreducible representations of the group GF, the p-adic group GF, to equivalence classes of Langlands parameters. That's what capital Phi is referring to, the set of such equivalence classes. And by a Langlands parameter, I mean an admissible homomorphism from the Vatelin group into the L group. The Langlands Correspondence claims that there exists a surjection with specific properties. And I'll say a few words about those properties over the next few slides. The place to begin in articulating those properties is to look at the fibers of this surjection. And the first claim that we find in the Langlands Correspondence is that these fibers are finite, and they're in fact parametrized by irreducible representations of this group, S phi. Again, in the case of classical groups, S phi is abelian. It's in fact a two group. So it might seem a little pedantic to refer to characters as to think about characters of irreducible representations. Why not just talk about characters of this group? And the reason is because, as I've said before, these groups, these finite groups S phi even, are generally not abelian. So because the Langlands Correspondence includes information about parametrizing the elements in the fiber by irreducible representations of this finite group, it's you can rephrase the claim that there exists a surjection with certain properties in terms of a bijection between, again, on the left-hand side, equivalence classes of irreducible admissible representations, and on the right-hand side now we replace the equivalence classes of Langlands parameters with equivalence classes of pairs, one being a Langlands parameter, phi, as before, and the other second component being an irreducible representation of this group that appears at the top of the slide. We can restate this again in terms of, and this is exactly what you see in the first theorem that I showed you from Arthur's book, in terms of a bijection. I'm talking, of course, for the Langlands Correspondence version of the theorem that you see in Arthur's book, in terms of a bijection from the L packet to irreps of S phi. And that means that there's a pairing, a function which takes elements from S phi and elements from the L packet and produces complex numbers. I call these the values of this function L packet coefficients. And that's because they are required to associate stable distributions to L packets, and when that's possible, and to A packets more generally. I'll say a few words about that later too. So here are some of the fundamental properties of L packets as they appear in the Langlands Correspondence. Well, the first is that if you restrict your attention to tempered representations, then on the other side of the correspondence, you find that your focus is drawn to Langlands parameters that are bounded upon restriction to they. So we get a remarkable statement that if you have one tempered representation in an L packet, then all the representations in the L packet are tempered, and you find a partition of tempered representations by L packets accordingly. And the corresponding class of Langlands parameters is exactly the one that I've already described. So that's the first important property. Second is that in that case, there is a stable distribution attached to the L packet, and it's given by the equation that you see in the middle of this slide. Specifically, it's these packet coefficients appear again. You can see that the packet coefficients are evaluated at this element S phi And so statement 2, as it appears here, is just that there exists an element SV such that this distribution is stable. You can, in fact, the element SV has a specific genesis in terms of an associated Arthur parameter. So, but putting that aside, again, we'll see a little bit more about that later. Putting that aside for the moment, what we see is that tempered L packets determine stable distributions by this formula. And the last statement that you see here has to do with a normalization of the parameterization of an L packet by irreps of SV. And specifically, if this normalization is chosen so that if pi is the word that appears in Arthur's book for this concept is unramified, also known as spherical, then the packet coefficients are trivial. Okay, so in summary, tempered L packets, somehow L packets are best behaved on tempered representations. They give you a partition of tempered representations, and they give you stable distributions attached to every packet. And these properties fail in general if you shift your gaze to non-tempered representations. Then you find that you can certainly still form the distribution up above, but it's not stable. So A packets are designed to solve this problem. If you go back and you look at this expression, what I just said is that if phi is not tempered in the sense that it's not an L parameter, Langlands parameter for a tempered representation, then this invariant distribution need not be stable. So A packets give you a way of solving this problem, and the way that they do it is an A packet adds to an L packet specific representations and extends the notion of these packet coefficients so that the same formula does define a stable distribution, but now the sum is being taken over all the representations appearing not just in the L packet, but in the A packet that contains it. Now, you have to be really careful interpreting what I just said, because I just suggested that every L packet is enlarged in some way to form an A packet, and then you get to attach a stable distribution to them. That's not the case. It's not the case in general. You have to. We only know how to do this right now. Actually, this is a key issue in the next talk. But right now, that statement is true for Langlands parameters that are Arthur type. And what that means is that if phi is of a certain sort, namely it's a Langlands parameter that comes from an A parameter, an Arthur parameter, then yes, the L packet attached to the Langlands parameter is contained inside an A packet, and the distribution that's attached to the larger set, the A packet, is stable. Again, in order to define that distribution, we have to say something about the packet coefficients. Okay, so this is the key feature that A packets are meant to address. So let me be a little bit more precise. So if you have an Arthur parameter, psi, then it determines a Langlands parameter. And I've denoted it by phi sub psi. And in that case, the Arthur packet should be thought of as an enlarged or an extended form of the L packet. I like to call the extra representations stabilizing representations. Actually, I used to call these coronal representations, but maybe in 2020 that's not such a great word, and also stabilizing is a little more descriptive mathematically. So what you see in the displayed equation here is precisely this idea that if you have an A packet, then yes, you can attach a stable distribution to the A packet, or let me say that again, if you have an A parameter, you can attach a stable distribution to the A packet. And the expression that you see for the stable distribution, it starts off by looking at the sum of the Hertzsprung characters appearing in an L packet, but there's an extra term that has to be added, and this is the sum that you see taken over stabilizing representations. So these stabilizing representations are the extra terms, the error, if you like, that's required to form a stable distribution from an A packet. Again, I want to give you an idea, for how this works using an example, and right away you'll see that this isn't actually an example because I'm using the definitely not classical group G2 over a p-adic field in order to give you this example. So this is I'll be talking more about this in the next talk, but nevertheless it exhibits exactly the features that I've just described, and in fact the point of the next topic is to claim that these should be called A packets. Okay, so here is a collection of 6 irreducible admissible representations of a connected reductive algebraic group. And of the 6, one of them, the one denoted pi3 epsilon, it's in fact a depth 0 supercuspidal unipotent representation, in this case of G2 over F. Okay, so the picture that you see, this is artist's impression of basic facts about L packets and A packets. The picture that you see is color-coded L packets. Besides each one of them, you see the corresponding symbol for the corresponding Langlands parameters. So the L packets that you see here, they're singletons in 3 cases, and there are 3 representations in this large L packet here. So these are L packets, and as it turns out, these representations are all of Arthur type, and that means they have A packets too. How do we go from L packets to A packets? Well, I already explained that you judiciously add to an L packet certain extra representations so that you can attach a stable distribution to the result. So in the case of this packet right here, you see no arrows colored teal, no lines colored teal coming out of this square. And that's telling you that it's already an A packet. In fact, these representations, these 3 representations are tempered. But the other 3, the red, the orange, and the blue representations, they're not tempered. So in each case, to go from the L packet to the A packet, you have to seek out these stabilizing representations. In the case of pi 0, there are 1, 2 stabilizing representations. And what that means is that pi 0 with these other 2, they form an A packet. You see right away, A packets are not a partition, unlike L packets. They definitely overlap. In this picture, you see that point made again. The circles now describe A packets, and in each circle you see an L packet, a specific L packet, and some stabilizing representations. Okay, note, this example shows many important features. Again, going back to the teal case, it's not teal, it's cyan, isn't it? Going back to the cyan case, this L packet is its own A packet, no stabilizing representations. Going to pi 0, the A packet for pi 0 is this red circle. It contains 1, 2, 3 representations. Note that it contains this L packet, but it also contains another L packet. So it's also not true that an A packet contains only 1 L packet. It's also not true that it's a union of L packets, because look at the way pi 0, the A packet for pi 0, it contains the L packet for pi 1, but it also contains 1 part, one third of the L packet for this representation. Same thing for pi2. Okay, so there are in this picture 1, 2, 3, 4 A packets that are built from 1, 2, 3, 4 L packets. Let me try and state Arthur's main local result a little more precisely now. The group WF that you've already seen a number of times, it's the Vogan group for the p-adic field F. WF prime, I've referred to it as the Vogan group, but in fact, it's the version of the Vogan group that's obtained by taking the Vogan group cross with SL2 and the finite dimensional representations of these two groups coincide. There's a missing prime right here, obviously. And the domain of an Arthur parameter is this group denoted W sub F double prime. So it's formed by attaching to this variant of the Vogan group another copy of SL2. So the domain of an A parameter has two copies of SL2 and the Vogan group. And that's exactly what you see here. An A parameter, an Arthur parameter, is group homomorphism from this group, W sub F double prime, into the L group with essentially the same properties that you expect to see if it was a Langlands parameter, except this extra condition 2, which is that the Arthur parameter is bounded on restriction to Vogan. That's a really crucial property. It's responsible for the fact that this rule that attaches Langlands parameters to Arthur parameters is an injection. And what that means is that Arthur parameters are reasonably thought as a subset of Langlands parameters. And this is why we can talk about Langlands parameters of Arthur type or not. Langlands parameters of Arthur type are a subset of the set of all Langlands parameters. They include all tempered Langlands parameters. I already mentioned those before. But there are many Langlands parameters that are not of Arthur type. This notion of Arthur type, Langlands parameters of Arthur type, if it's hit by this map, this injective map from Arthur parameters, and the corresponding admissible representations are said to be of Arthur type again if their Langlands parameter is of Arthur type. That's unsatisfactory because it would be better to have an intrinsic characterization of that's showing how you recognize an admissible representation as Arthur type or a Langlands parameter of Arthur type. That turns out to be very subtle and not so easy to do. And we'll get into that in this talk. Okay, so we've been talking about L packets. Now let's and A packets, but let's pay attention now to the finite group that whose irreps parameterize an A packet. That's a shockingly familiar looking group in the sense that all that's happened here is we've replaced the Langlands parameter phi with an Arthur parameter group psi. And so again, thinking about the theorem I showed you from Arthur's book, what you see is that an A packet is a finite set and it comes equipped with these packet coefficients, or this function that gives you packet coefficients. We want it to be precise, we would talk about A packet coefficients, since I've already talked about L packet coefficients. Right, so that you right away, I'm sure you're thinking about, well, wait, if an A packet contains an L packet and there are packet coefficients attached to the L packet and there are packet coefficients attached to the A packet, maybe one should be an extension of the other. And that is in fact the case. The L packet coefficients are extended to define A packet coefficients, right? Why? You can see that's implicit in what I've written here. It's not implicit. It's no, it is actually. It's exactly the fact that I wrote these coefficients as A packet coefficients and then rewrote that sum with L packet coefficients is exactly telling you that A-packet coefficients extend the definition of L-packet coefficients. And that stable distribution that I showed you just now appears here again. And so this is a theorem that tells you how to attach a stable distribution to an A-packet. A-packets are parameterized by A parameters, Arthur parameters, and each one contains there is an L packet in each one that's attached to the Langlands parameter, to the Arthur parameter. So the stability result is a crucial result. The example that I gave you earlier in this talk dispels some common misapprehensions about the coefficients that appear in these stable distributions. Are they all positive? No. Are they all Are they all like just sums of characters of admissible representations? No. There's this 2 that appears even in the case of this tempered packet. Now that's a phenomenon that doesn't show up for classical groups. Remember that G2 is the group in play here. But note that these stable distributions that are attached to A packets, these four A packets, the coefficients are interesting. Okay, so this theorem exactly states what I promised you a moment ago, which is that the packet coefficients that appear in Arthur's result, they're an extension of the packet coefficients that appear in the local Langlands correspondence. It's in this sense that we recover the Langlands correspondence from the main local result that we saw up above in the case of Langlands parameters of Arthur type. So 2 constraints, right? One is we're talking about classical groups, and we're talking about admissible representations of Arthur type. The defining property of A packet coefficients is the theorem that you see stated here, and it's the theorem that refers to endoscopy. So the statement is actually quite simple. It says that if you have a semi-simple element that commutes with an A parameter, that's the statement right here. S is in the centralizer of the Arthur parameter, and if you use the packet coefficients to define this distribution, capital theta some psi comma s, then that distribution is a lift of a stable distribution from an endoscopic group, and that's what this theorem here is saying. It's telling you that if you start with an A parameter for an endoscopic group for G, and then you lift that to an A parameter for G, then these distributions, they're related by Langlands-Chelstedt transfer. So these 2 values are the same on all functions that match in that sense. But notice that the distribution on the right is, by what I've told you up above, a stable distribution attached to an endoscopic group G prime, whereas the thing on the left, it's a distribution of the sort that you see up above, and I didn't claim that they're stable, and in fact they're not stable in general. So if you think about this in terms of lifting the actual distributions, it's telling you that the stable distribution on an endoscopic group lifts to a not necessarily stable distribution on G, but they still match in this sense. Okay, so I said this a moment ago, Arthur's main local result is that these A packet coefficients are in fact uniquely characterized by this theorem that appears right here, this matching theorem that refers to Langlands-Chelstedt transfer from an endoscopic group from G to G prime. Okay. I want to say a few words now that form a bridge to the next talk, but to do that, I'd like to go back and remind you where we began, which is talking about tempered representations. I mentioned earlier that this function from A packets to irreps of this component group SV, neither injective nor surjective in general, and we don't even have a definition of A packets for representations that are not of Arthur type. So question, what do we do if groups are not of classical, and what do we do for representations that are not of Arthur type? There's an answer to both of these questions. In the early 90s, David Vogan provided an alternate, very geometric approach to thinking about local Arthur packets. I'd remind you that Arthur packets were introduced and originally globally in the late 80s. It wasn't long after that Vogan said something about local Arthur packets that was purely intrinsic and geometric, and it was very difficult to compare these two notions until Arthur's book in 2013, because it wasn't until then that we actually had a local characterization of local A packets. So in this slide, I'm promising you that there's a way to define for any Langlands parameter phi and for any connected reductive group G an enlarged version of the L packet, should we know it. And the recipe that I'm referring to, it's expanded upon in this paper. It's written with a small army of my collaborators, and it's coming out in Memoirs of the MS, but it's still in press. It's available in the archive. It tells you how to define this, what we call an ABV packet attached to an arbitrary Langlands parameter for an arbitrary connected reductive algebraic group. Raising the question, is it the case that for classical groups and for representations of Arthur type, do these two constructions agree? And we conjecture that that's the case. We know it's the case in many, many examples, but we haven't written down a proof. We're working on a proof of these conjectures, starting, of course, with general linear groups and then going on to groups of type B, C from there, and ultimately D. But the next talk is about G2, and it makes no sense to seek this comparison in the case of G2 because we don't have Arthur packets for G2. So the strategy that I'm espousing here is that we might use Vogan's perspective to actually define Arthur packets for G2 and then justify calling them Arthur packets by showing that they satisfy the same properties and hopefully uniquely defining properties that I explained in this talk that come from Arthur's main result on local fields for symplectic and orthogonal groups. Thanks very much.